So we need to go from the right to left. So what happens is 0, 1, 0, 1, 1, 1. We have to group for 3 bits each, and we have to proceed and put the uh, answer in the order. So what happens is 0, 1, 0 means 2, 1, means 7, 1, means 7, so on till 3. So this is the answer, final answer. This is all about the conversions of the these are all the conversions among the binary this number systems, from binary to octal, octal to binary, all hexa to binary. All the conversions we have considered over here, and we have got the results. Now we are going to the arithmetic part, which is for unsigned numbers. Now we are considering two operations, that is binary addition, binary subtraction. Now we have, let us for this we need to go for a truth table, that is 0 plus 0 is equal to 0, 1 plus 0 is equal to 1, 0 plus 1 is equal to 1, and 1 plus 1 is equal to 1, 0 in the case of binary addition. So by using this table, we are going to find the result. So now we will start. We have taken one example where we are having both this fractional part also. So when you are adding, when we start doing from the left to right, right to left, when we start doing it, we get the answer as 1 plus 1 is equal to 1 plus 1 is equal to 1, 0. 0 is written in the result, and 1 is carry. So 1 plus 1, again it will become 0. Again 1 is carry, and the 3 ones, 1 plus 1 is equal to 1, 0. And if you add 1 again after point, before point, 1 plus 1, so we have 1, and when you add 1 again it becomes 0, and when we add 1 it becomes 1, and 1 plus 1 will become 1, 0. That is what regarding the binary addition. Coming to binary subtraction, it is a simple method as how we do normally, that we have done. But whenever there is a carry, then we are going to add that carry also, and we are writing the answer. So 1 plus 1 is equal to 1, 0 in binary addition. That is what the result is. Coming to binary subtraction, now what happens is you are separating two numbers. So again we will go from the right to left. So 1 minus 1 is equal to 0. Again, when here 0 in second rightmost one, second bit in the rightmost, when you are subtracting from 0 minus 1, we cannot do it. So again, as usually we will, as how we do for the normal subtraction, we will take a borrow from the next number, very next number. So we took the 1 is there, so we took the borrow from there, and in that 0 will become 1, 0. And from 1, 0, if you subtract 1, it should become actually 1, but written 0. It should be corrected. And here the 0, this binary subtraction is having some problem. We will look it afterwards. And next, now coming to the complements, there are two types of complements with for base R. The types are R and R minus 1's complement. For decimal number base 10, it has 10's complement and 9's complement. There are two types of complements for base R. The types are R and R minus 1's complements. For decimal number base 10, it has 10's complement and 9's complement. For similarly, for binary number, it has 2's and 1's complement. So the formula for finding R's and R minus 1's complement is R's complement of n is equal to R to the power of small r to the power of n minus capital N. That means small r is nothing but it is the base of the given number. Small n is the number of integral digits. Capital N is the given number for which you have to find out the complement. And again, for r minus 1's complement, we have capital N is equal to r to the power of n minus r to the power of minus m. This is the formula where m is the number of fractional digits. Now performing subtraction using complements. The subtraction of two n-digit unsigned numbers m minus n can be done using base r and r minus 1. So now how we are going to perform the subtraction using complements. So subtraction using r's complement. So if you are doing that, we need to follow some steps for separating two numbers by using r's complement. What we should do is, we have to suppose there are two numbers m and n. M is the minute and n is the subtrahend. M is the first number, it is called as minute. The second number n is called subtrahend. First we will take the m and we will add the r's complement to the subtrahend. So when you do that, if then you have to observe the result. If there is an n carry in the result, you have to neglect it and you have to write down the directly the result. If you don't, if you have any n carry, you have to neglect the n carry and write down the result. If there is a end carry, if there is no end carry, else if there is no end carry, then what happens? You have to take again the r's complement of the sum. After get the sum is there now, again you have to find out the r's complement for that sum and you have to put a negative sign in front of the result. That is what we have to do for if we don't have the end carry. Similarly, if you go for the again we are doing the following the steps for subtraction using r minus 1's complement. In this again we will do the similar way. What we will do is, we will add the minute m to r minus 1's complement of the subtrahend n. And if end carry occurs, what happens is, in the previous case, if end carry is occurring, for r's complement we are neglecting it. But in this case, if you are having any end carry, that end carry has to be added to the least significant digit. Least significant digit. Least significant digit means the digit which is at the right side, which is having least significance. And most significant bit means it is the number which is on the left side, which is having most significance. So the number at the rightmost digit, you have to add the end carry when if there is any end carry occurring, and that will be your result. If there is no end carry, what you will do is, as usually, again you have to find out the r minus 1's complement of the sum and you have to place a negative sign in front of the result. That is what the subtraction by using the complement. It can the same way in this r and r minus 1 for base, for decimal number, the r will be 9 and 10. R minus 1 and r will be 9 and 10 for decimal number. For a binary number, r minus 1 and r will be 1 and 2. That is what for binary number. Now let us take an example. The procedure is being told and we are just performing the subtraction by taking an example. So using tens complement, perform 72532 minus 3250. And now what happens is, let us take m to be 72532 and n to be 03250. Means we are placing 0 because of the bit size of m. So what happens is, now 10 to the power of 5 means the formula is already known to us, r to the power of n minus capital N. R means here it is equal to 10. So n means the number of digits, that is in the integer digits. It is how many? 5 are there. 10 to the power of 5 minus 03250 minus 03250, it is equal to 96750. 96750. So what happens is, m plus now tens complement is obtained, and now what we are doing is m plus tens complement of n, that is m is equal to 72532. We are adding tens complement of n. So what happens is when we are adding, we are getting an end carry. That end carry has to be removed, and you have to consider only 49282, which will be the answer. That is how we get. So now next one is using tens complement, perform 3250 minus 72532. So let us take that one, and m is equal to 3250. Tens complement of n is equal to, now we have the interchange the values for m and n. So now this time we are going to find out the tens complement of n, that is equal to 72532. Again for this also we are going to find out, and what will be the answer is 10 to the power of 5 minus 72532. So we are getting it as the 27468, which is the tens complement of n. Now if you add both m plus tens complement of n, when you are adding both, what is the answer is 30718. In this case, we are not getting any end carry. When we don't get any end carry, what we should do is, again we have to find out the tens complement of 30718 and put a negative sign in front of it. So what happens is, again we are trying to find out for 30718. This time for that we get it as 69282, and we are putting a 9 minus sign here, so it is minus 69282. This is what. So again for using 2's complement, we have to perform the first case we did it for the decimal number. Now we are trying for the binary number. Using 2's complement, we perform 1010100. In this, what will happen is, again we are taking the first number m as m and the second number as n. So the second number we have to find out the 2's complement of n. So how many bits the size of the bit is 1 2 3 4 5 6 7. So we have the size of the bit is 1 2 3 4 5 6 7. So 2 to the power of 7 minus the given number. So now when we add m plus 2's complement of n, that is equal to m is equal to n plus 2's complement of n. So what happens is, when you add these two numbers, we are getting the carry, and that you are discarding it. Now the answer is simply we are removing the 2 zeros, and we are writing the answer as 1 4 zeros. That is what we get it. And after that, for using 2's complement, perform next problem. Here in this problem, we are just reversing the values. Again m became n became m. So again this time we are taking the 2's complement of n. Again what happens is, we are adding the both. Again in this, after addition of the both, we are not getting any end carry. If we don't get any end carry, again we have to find out the 2's complement of the answer, and we have to put a negative sign in front of that. So when we get the 2's complement, we got it in that way, and we are putting the result as a negative value, and that will be the answer. This is how we have to perform the subtraction using the complements, r and r minus 1's complement. This is the complements application is to perform the subtraction. Now arithmetic with sign numbers. Arithmetic with sign numbers. So earlier we discussed the arithmetic with unsigned numbers. Now we are discussing the arithmetic with the signed numbers. If it is unsigned numbers, simply we take the number normally and we will do it. If it is in binary representation, simply we can add and subtract if it is in binary representation. But when we consider the sign number, we have to consider the sign also, and we have to represent the sign also in the bits itself. That is what we have to think over it. So coming to the positive signed binary numbers, positive integers include 0 can be represented as unsigned numbers. When we don't have any, if you consider an unsigned number, just you need not consider anything, just you can put a 0, which will specify or represent that this is a positive number, because we are putting a 0 in front of the unsigned number. When we want to represent a negative number, we need to put a notation for negative values. Generally, what happens is, for negative values, it is indicated by minus sign, and positive number is indicated by plus sign generally. But in computers, the negative sign is also represented with binary digits. What happens is, generally when it is a negative number, you put a minus in general case. But when if you think when you go for the computer cannot think in that way. So we should represent the negative sign also with some bits so that the computer can understand. Uh, the computer cannot understand the symbols. It is customary to represent the string with a bit placed in leftmost position of the number. The tradition is to make a sign with 0 for positive and 1 for negative. When the number is positive, you put it as 0, and if the number is negative, you put it as 1. So where we are going to put the zeros and 1, that we are going to see. If the binary number is signed, then leftmost bits represent the sign, and the rest bits represent the number. As I have told you, leftmost bit has to be which will represent a given number. Which if it is a if leftmost bit, if it is 1, the number will be represented as negative number. If it is 0, the number will be represented as positive number. So when a sign number is given to you, and if leftmost bit is 1, you have to think it is a negative number. Otherwise, it will be a positive number. So that is what the remaining bits other than leftmost bit will be the magnitude or value of the given number. If the binary number is assumed to be unsigned, then the leftmost bit is the most significant bit of the number. So if it is unsigned number, then the leftmost bit will be the most significant bit number. That is what. So when we are considering the arithmetic with signed numbers, there are three different ways. First one is signed magnitude representation. Second one is signed ones complement representation. The third one is signed twos complement representation. For example, if you are considering an example of -9 for 8-bit representation, how we are going to represent -9 in signed magnitude representation, that we are going to see. The leftmost, now for this, as it is a 8-bit representation, as it is a signed number, -9 is a signed number, what we will do is the leftmost bit will be 1 because it is a negative number. So that will be, we'll putting 1, and after that the remaining rest of the bits after 8 minus 1, the 7 bits will be the magnitude of the given number. That is, you can specify the 9 in terms of binary. That is 1001. All the remaining are zeros. Now that -9 is represented as 1001 in sign magnitude representation. Just a sign is there which will tell that the leftmost bit is the negative number, and remaining you are writing the 9 in the rest bit. Coming to signed ones complement representation. Here what happens is we have to take the ones complement of the sign magnitude representation. So what happens is the sign magnitude representation means you have to take the sign magnitude representation of 9, not -9. For that you have to find out the ones complement. So first you take the ones complement of +9. What happens is generally for +9, if you take the sign magnitude representation as it is positive number, the leftmost bit will be 0, and after that you will be writing the 9 value in the binary form. So what will be the ones, what will be the actually, it will be like 0 0 0 0 0 1 0 0 1. That is there. Here the leftmost 0 represents what? It is represents the sign of the positive number of a 9 is positive. But for this, if you want to find out the ones complement, you should represent as, so what will happen? Similarly, for a complement, ones complement means all zeros becomes 1 and 1 becomes zeros. So what happens is all 4 ones, 0 1 1 0. Generally remember that for any ones complement number, there is no need to go for the complement formula, a long formula. Just you can what you will do is, if zeros are there, that will become 1, 1 is there, it will become 0. There is no need to go for the r minus 1's complement formula. That also will give the right answer, but simplest way is 0 will become 1, 1 will become 0. Similarly, for 2's complement also, what you will do is first you find out the one bit for one's complement. After finding the one's complement, just add 1 to the rightmost bit. Rightmost, that is least significant bit. If you add 1 to the least significant bit, then automatically you will get the 2's complement. That is a shortcut method to find out the 2's and 1's complement. For 10's and 9's complement, you have to go for the formula. But for 1's and 2's complement, just is the shortcut method. So what we will do is, we for minus 9, if you are asked to find out the signs 1's complement of minus 9, first you consider plus 9, and then what you have to do is then find out the sign magnitude representation for that, and then you try to find out the complement of that. That will give you the 1's complement representation. Similarly, for 2's complement representation, as I just told now, what you will do is you'll first find out the 1's complement representation, and then you'll add the 1. And for that, at the rightmost bit, then you get the answer as 1 1 1 1 0 triple 1. Okay, that is how you find out the sign magnitude, sign 1's complement and 2's complement representation for the given number 9. So that is what we will do. So for representation of negative numbers, sign magnitude method is easy to understand. Among these three methods, the first method is very easy. Simply you will put a 1 or 0 and you write down the remain. There is no need to go for the complement for the sign magnitude method. But the thing is, however, it does not work well for computer, especially when we need to perform addition and subtraction. What happens is, when we need to add or subtract, this particular sign magnitude method will not work properly. Because if you want, we can take an example, we can see whether it will work or not. So for plus 7, because it is plus, we put it 0 and remaining 0 triple 1. Here we are considering the 5-bit representation. You can consider any bit representation. You will take the size and you can add number of zeros, and you can just put any bit representation. You'll get the same answer. So there is no any particular formula for representation of the bits representation. So what happens is, now here for plus 7, you took as 5. You can take it as 6, 7, 8, it's your wish. But leftmost bit should be 0, means it is positive number, 1 means negative number. The middle number, 6, your wish. How many you want, you can put it, no problem. But the leftmost bit will be the sign representation. So now plus 7, 0, 0, 1, 1, 1 means 0 will be the positive number, minus 7 means negative number, 1. So we have taken that way and we have added by using sign magnitude representation. But in this case, what happened? 7 minus 7 means it should be equal to 0. But what we got 32, which is not correct. So the sign magnitude representation will not work well when we are performing addition or subtraction. So what we will do is, we will take the third one, that is sign 2's complement representation method. In this method, we are going to add both and see. So what happens is, now for plus 7, what we'll do? We will take it as plus 7, generally it is 0, 0, triple 1. Okay, no problem. For signs 2's complement of minus 7, it is 1, 1, 0, 0, 1. So now we will add it. After addition of this, what we have? We got the, what this carry end carry. So when we get end carry, already we are aware of that in 2's complement, r minus 1's complement. When we have an end carry, we have to discard it. So we will neglect it, and the answer is remainder zeros, which is the correct answer. That is what we get. So now we are taking the 42, 24, 2's complement of that, and just we are checking for 42 minus 24, we got it as 8, which is correct. This is what we have to do. That is okay. And next we are going for the arithmetic subtraction. Arithmetic subtraction means this operation can be changed to an addition operation if the sign of the subtrahend is changed as it is demonstrated by the following relation. So now if you take a plus or minus a minus plus b is equal to plus or minus a plus minus b. That means if you are having that number, you can just take the minus and you can put inside the bracket, and just you can represent with plus. That means the subtraction also can be represented in the form of addition, and that negative number which is over inside, that can be taken as directly. You can find the 2's complement for that, and then you will get the simplified answer easily. So now let us go. If you take an example of minus 6, minus of minus 13, which is second case, how plus or minus a minus of minus b, in that way the example is also there. So when you have like this, minus 6, multiply minus and minus plus 13. So 13, as usually you will write in sign magnitude representation. 13 means sign magnitude representation, it is 0. So all you put 0, 1, 1, 0, 1. Whereas for minus 6, you would write the sign magnitude representation of 6. 6 means how much? 6 plus 6. Plus 6, you have to find plus 6 means how many? 1, 2, 3, 4, 5, 6, 1, 7, 8. Means 4 zeros. After that 0, 1, 1, 0. That is the sign magnitude representation of minus 6. 1 plus 6 means 4 zeros, 0, 1, 1, 0. After that you have to complement it. It will become how much? 4 ones, 4 ones, 1, 0, 0, 1. Again, if you add 1 for the rightmost bit, then it becomes 1, all ones, 0, 1, 0. This is what we have. And if you take it and if we add it with 13, we get it as, we are getting an end carry of 1 and 0, 4 zeros and triple 1. So this end carry can be discarded and you will be left with 1, 1, 1, that is plus 7. So that is the right answer for the arithmetic subtraction of minus 16 of minus 13. That is